Hi, I am Vibhav, and today I am going to talk about the design of the CPU and how this can be translated to an HDL code. This diagram is the proposed design for the CPU architecture in which I am going to use to implement and explain the HDL code of the CPU. In the following diagram, the CPU consists of several logic gates such as the ALU, A register, D register, PC, and the multiplexer. Since we have built most of the logic gates from the previous tasks, in this unit it will be easier to implement the CPU HDL code with them. The first step to implement the HDL code is to derive the API of the CPU. The API specifies the chip name, the input and the output pins, and the function of the CPU, and moreover also an additional comment. And so for now, let us not think too much of the logic gates inside the CPU chip and start off with an abstraction of this chip by hiding all the logic gates in the diagram so that we can easily identify the input and output pins of the CPU. Now we can clearly see the input and the outputs of the CPU. As shown in these diagrams, there are three inputs coming into the CPU from different sources in the computer: the instruction memory and the data memory. These inputs are the instruction in M and reset. The instruction input is from the instruction memory or the row, which is the value of the selected instruction memory register. This instruction can either be an instruction or a C instruction. On the other hand, in M is the value of the currently selected data memory register and is the value that the CPU uses to perform its operations. Here we can really see a diagram that further shows that the CPU is connected to the instruction memory and the data memory. This diagram was used to implement the hack computer in one of the tasks that I have done previously. Here we can really see that the CPU takes its instruction input from the instruction memory and also takes the value of the selected data memory register as one of its inputs. The reset input is the value that tells whether we bring the CPU back to its initial state or to be specific to start off the operation of the CPU all over again. Furthermore, along with the inputs, the CPU has several outputs that are connected to the instruction memory and the data memory as well. These outputs are called as write M at M address M and PC or the program counter. Going back to the given CPU architecture, we can see that the ALU gives an output that is written to the data memory. In order to do so, the ALU must specify few things. Firstly, the content that the CPU is going to write in the data memory, which is stored in the out M. Second, the address of the write operation in the data memory. Basically, this is where we want to put the content in the data memory. Lastly, the output that allows the CPU to write the content to the data memory write M. The program counter holds the address of the next instruction, which will then be fetched, decoded, and executed by the CPU in the next cycle. Now that we have identified the inputs and outputs of the CPU architecture, we can now implement the code of the CPU. This is the HDL code of the CPU that was provided in the task resources. I will explain this code to you in more detail by parts as I go along with the presentation. Here we have the header section that specifies the CPU interface. It consists of the chip name and the names of the input and output pins. Since we are implementing the CPU chip, the chip name that we are going to write for this code is CPU, as shown in this code. The input pins of the CPU will consist of 16-bit nanometer, 16-bit instruction, and reset. On the other hand, the upper pins of the CPU will consist of 16-bit out M, write M, 15-bit address, and 15-bit PC. The input and output in this header section of the CPU do correspond to the design that was shown and discussed in the previous slides. This is the first part of the part section in the CPU HDL code that I have shown previously. As you can see, we have three different gates: NOT gate, AND gate, and MUX16K. These gates allow CPU to function and perform specific operations. Firstly, there are two types of instruction coming into the CPU from the instruction memory. These instructions are the A instruction and the C instruction respectively. Here, I will explain the A instruction and the C instruction in more detail. A instruction has symbolic syntax of add value. This value can either be a number, that is a decimal non-negative number, or a symbol. If the value of A instruction is a number, then the instruction will set the contents of the A register to the specified value in the instruction. But if the value of the A instruction is a symbol, then the instruction will set the contents of the A register to the value that the symbol points to, and this value will not be the actual value in that memory register. On the other hand, C instructions has a symbolic syntax of test equal to comp and jump. This instruction performs a computation on the CPU, which is stored into a destination register or a memory location. It can also tell the CPU to jump to another instruction memory address that is pointed by the value or the symbol. In the first line, NOT gate is used to tell whether an instruction coming into the CPU from the instruction memory is an instruction, but first the CPU decodes the 16-bit instruction into an opcode and 15-bit value. If the opcode is 0, the instruction is an A instruction, whereas if the opcode is 1, the instruction will be an C instruction. For instance, if the instruction coming into the CPU from the instruction memory is an instruction, the CPU takes the specified 15-bit value and stores the value into the A register. However, as you can see in the diagram that was taken from the CPU architecture, the A register can be fed either the instruction input or the all output. If it is a C instruction, it performs the computation. In the ALU, output is fed to the ALU and the ALU output is fed to the A register. We use the AND gate to determine that the instruction 16-bit multiplexer is also used to select whether the instruction or the ALU output is stored in the register A. In the next part of the code, we have got an OR gate. The load bit in the A register would be 1 if either the A instruction or the ALU output is fed to A. On the other hand, the A register is used to store the value that is fed into the A register. It takes in the output A register in from the multiplexer and the output load A from the OR gate as its inputs. The output A out then generates the content or the value that is currently stored inside the register. Next is another MUX16, which takes in the output of the A register and the value that is currently selected in the data memory register. In M, this will select which one to output A or M. Either A or M will fed into the ALU depending on the 12-bit instruction value. The AND gate is employed to determine whether the ALU output is loaded to the D register. The D register is then implemented to load and store the value of the D register from the ALU. Next up is the ALU gate. The ALU computes a function on two inputs, which in this case would be the value that is stored in the D register and the value of either the A register or M register, and then generates output. It consists of input control bits such as the ZX and XZ, YN, YF, NO, which are indicators of which function is computed on the two inputs to produce output, whereas the output control bits such as the ZR and G determine the properties of the result. The following code, which consists of 2 or 16 and A, and gate sets the ALU outputs in order to successfully write on the data memory. The first or 16 code line determines the address of write operation. In the second one determines the content of the data memory. And lastly, an AND gate that outputs value that allows CPU to write the content to the data memory. Program counter, or also known as PC, is a register which contains the address of the instruction to be fetched. Next, in this part of the CPU HDL code, the load bit of the PC is determined by the jump bits and the ALU outputs. Basically, these lines of code determines jumps conditions and checks the ALU output to see if the conditions are met. If the instruction is the instruction and the conditions are met, the program counter is loaded with value that will ask the CPU to jump to the specified value or symbol. If the PC is not loaded, then PC is incremented. Incrementing means that the CPU will read the next instruction. And so this is how I understand and implement the HDL code for the hacked CPU. Thank you. Here we put an end to the presentation.